Hello and welcome to tutorial 12 of this course, Reinforcement Learning. I am Abhik Kaur, a PhD student at Indian Institute of Science. Today we'll discuss partially observable Markov decision process, or in short, POMDP. So many of you, I think, already has a background in machine learning, and there you might have studied hidden Markov model. So we'll discuss what is that, but before beginning, we'll just make a statement that partially observable Markov decision process, or MDP, is actually a controlled hidden Markov model. What does that mean? There is something called hidden Markov model, and there is a control element to it that makes the entire thing partially observable Markov decision process. Now, let us draw a diagram which will depict what partially observable Markov decision process is. Okay, before that, let's just draw an analog. So POMDP is controlled Markov model. Then this is basically an analogous statement of this statement. MDP is controlled Markov chain. So this you can think as a block diagram of partially observable Markov decision process. So there is an underlying Markov chain. Or you can say that this is an MDP rather. So MDP. It has a current state, say X T or XK. And we cannot observe the state. So it passes through some kind of obstacle. We can think that obstacle as some noisy sensor. So state is a process which we have to sense. So for some systems, state can be temperature, pressure, or some other physical variable, position, velocity. So that has to be measured, right? So there will be sensor, and sensor might have some noise. So what uh, makes it partially observable is basically some noisy sensor which cannot sense the true data, rather it sends something noisy. And that's our observation. This is one way to think that state, and this is observation. And okay, so MDP takes an action. You choose an action to play, and based on that, the MDP updates its state from XK to it goes to XK plus 1. And here we are assuming that how we'll sense the data or how we'll observe the data. That also depends on the action. So, for example, in communication field, if your receiver is your transmitter using more power, then the channel loss will be less, and hence your observation will be closer to the state. So your action is actually uh, manipulating your observation in that sense. And here is some decision maker controller, which is seeing this YK and some additional information. Now, this is YK. This is some additional. Now, what this additional info will be, based on that, we have different type of uh, controlling method of POMDP. So today we'll mainly discuss which is called belief states. So instead of writing like this or drawing like this, um, we can add another block which will generate the belief state. Some pi k, and this from hidden Markov model literature, this is called HMM filter. What it does is, based on your current observation state and action, it generates the belief state. It's called HMM filter. And this belief state is fed to the controller, and controller takes an action, chooses an action to play. Now, this belief state has big role, a big role. I'm coming what that role is. Or this is also called posterior. Okay, so the main statement here is belief state makes the POMDP an MDP. So it transforms. But there is a cost associated with that. Beliefs, even if the true MDP has finite finite number of states, the space of belief state will be infinitely large, or that is basically the uh, space of simplex. I'll explain all these things one by one. But there is a cost. That's the main takeaway. Okay. So before going to further theory, let me just introduce the notations. So far there is no question, right? So this calligraphic X is denoting the state space. 1, 2, dot, 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 capital X. So capital X is the cardinality of the state space, which is finite. And we denote the state at time k as xk. So xk belongs to the set X, state at time t. So let's just note that the system is finite horizon that we are assuming. And there is action space U, or let me just change it to A. So here also we are considering there are finite number of actions. And similarly, AK belong to the set. It's the action at time K. There is an observation space denoted by calligraphic Y, similar to X and all. You can denote it by this 1 to Y and YK. So observation at time K. So in MDP, you have come across transition probability matrix. Here also you have transition probability matrix that. So it's joining. Okay, so in MDP, we have seen transition probability or transition probability matrix. So here also you have transition probability matrix. Pij U, that denotes the probability that xk plus 1 is equals to I or j, given xk is I and action at time k is a. So this is the transition probability. And this is for state transition. But these states are not observable. State transition probability. And there is something called distribution, observation distribution. So that is denoted by B I Y A, which is basically the probability that Y K plus 1 is small y, given xk plus 1 is I and ak is a. As I have said earlier, that in the diagram, so this action, so ak is action. The action is influencing the MDP to change its state, as well as the action is also influencing the sensor so that the current action, so that xk plus 1 and ak, both of them influences yk plus 1. And that's what we have written here. And I have given already an example that the observation can also depend on the previous action. For example, in communications, uh, the transmission power, which is an action, uh, that uh, increases the uh, probability that the receiver will see the true state or the true information with high probability. So in that case, the observation will be closer to the uh, true state with high probability if the transmission power is high. Okay, so then there will be reward or cost, anything will be fine. So R X K A K reward obtained at time K. And so this is a finite horizon setup. So we also have a terminal reward. So N is the horizon length. So this is the terminal reward. So let me write this the dynamics of partially observable Markov decision process as an algorithm. So the time will evolve from 0 to capital N at time k equals to 0, 1. So N. Well, so first there will be initial state that I should have written at time k equals to 0, where is state x naught, which we can think as which is sampled from initial distribution, state distribution pi naught. And next, for each time, we have a set of information. So, say for example, I at time t equals to 0, we just have x naught or pi naught. So pi naught is the distribution we can, since we cannot observe x naught, so uh, let's just uh, see keep the pi naught here because we don't have x naught. And for ik, we have the information pi naught, q naught, first observation, then pi 1, so q1, qk minus 1, yk. Well, so think I should not have written pi here. It should be y. Okay, so and it takes action and controller takes action UK, which is there is some policy mu k, and it is basically history dependent. It sees in all the information gathered till time k and takes a decision. And this decision is okay. So I am denoting AK, right? The action is A. Well, next, the decision maker incurs a reward. Gets R of XK AK time K. Then the state evolves. How? 6K plus 1 is sampled from this distribution, right? Scale. Right. But this is not observed by the controller or the agent. Let's just use controller throughout. The controller observes yk plus 1, which is again sampled from this distribution. K plus 1 UK. So this is P dot XK UK, and this is P dot XK plus 1 UK. Sorry, AK. And we have gathered new information now. So I K plus 1 is now IK union with UK and YK plus 1. And then it repeats, and in the last step, it incurs R of Xn, but because that is the terminal reward. Well, so here the policy was, you're assuming this is non-stationary, mu not mu1, so mu n minus 1. So non-stationary is would be the right assumption because these are history dependent policy. So it's taking the history and giving output action. Okay, so what is our objective? Similar to our MDP, the objective is to maximize the reward. So for a policy, mu, we write the reward as V mu initial state distribution, V mu pi naught as expectation taken with respect to the policy mu, sum of rewards plus the terminal reward. And okay, so given the initial distributions, and this is denoted for a policy, and the aim is to find the best policy. So the policy which will uh, maximize this for any point is called optimal policy, or yeah, optimal policy. And there is no guarantee that the optimal policy, there will exist an optimal policy that will be stationary or uh, Markov. Markov means it depends on the last step only. So there is no guarantee in form DP. Okay, so now let us come to what is called belief state. So here we have seen that since we have there is no guarantee that Markov policies are optimal. So instead of so for a POM-DP, the optimal action that is chosen by the controller, that is of the form increase turn, okay, where I guess the information delta in K. And in MDP literature, we have seen that AK is, this is for POM-DP. And in MDP, we have seen AK is star X key, right? So where X key is the state. Now, the question is, can we do something to make the system Markov so that the optimal policy will also be Markov. So that's the main question, and that's the reason behind why we uh, go for belief state. The idea is very simple. That is to keep maintain a posterior distribution of the current state given the information. So belief state is nothing but this thing. K is nothing but okay. So this is, let me first write this. This is a probability vector on. So delta denotes simplex. That means I'm coming what that means. Simplex over the state space. So this space means theta belongs to this simplex. It means sum of theta i's I in x is 1 and theta i's are greater than equals to 0 for all I in x. Basically, all the probability, all the PMFs on the state space. So belief state is a element in the simplex. This is this space of probability kernel, probability mass functions are called simplex. Now, this particular element in the simplex is that this denote probability that xk belongs to, sorry, so pi k of I means so the PMF is a vector, right? Uh, so I is the ith element or probability of the I uh, state I. So it's basically denote what will be the probability that the state xk is equals to I given the information we have gathered till time k, where I is a state and ik the information till time k. So now, if you have studied hidden Markov model, you know that uh, we can write this recursively. So we can write pi k from pi k minus 1. Given that we know the this two things. What are the two things? This transition probability matrix and the observation distribution. So P, what should I write? Yeah, just P. Let's write P and B. If we know this, then we can exactly compute the belief state from the previous belief state. Now we know that pi 0 is the initial distribution. So this we know, right? Pi 0 is known. So let us compute what is pi 1. So what will that be? So say we have taken action. We have taken action A not, right? So first summation will be, say, first summation will be on S. So phi probability that phi 1 I is probability that x1 equals to I, right? Let us use conditional probability is x1 equals to I given A naught is A and x naught is I. Sorry, so G. And sum over all A and J. So this we have written in conditional probability. So we have to multiply something, right? So probability of A given B. So probability of A equals to probability of A given B times probability of B by probability of, sorry, what I'm writing. So this will be I, and so did I write it correctly? And this can be further written as well. So this pi 1 is also depending on y. So we have already observed y. So there is something more complicated will happen. So this is wrong. So pi k plus 1 I is the probability that xk plus 1 is equal to I, given yk plus 1 ak and also xk. Okay, so sorry, xk is, we have not seen that. I came like, so yk is something we have seen. There is some complications in. So probability of xk plus 1 equals to I, given we know this yk plus 1 given y xk plus 1 is I and ak equals to a. This probability we know, but to decompose it, we need something like this xk plus 1 equals to I, given yk plus 1 is y, and ak equals to a. So how do you do that? I think Bayes rule is the answer. See, this we have we want. So A given B is probability A intersection B by probability of B, right? Now we have something, we have some hope that we can write it as yk plus 1 equals to y given xk plus 1 equals to I, ak equals to a. Then we have to multiply something, right? Okay, let's see now if we can use this thing. Pi k plus 1 I is probability that xk plus 1 is to I given so first decompose pi k j x. is divided by k plus 1. So I think I'm messing it up. There should be something easier. Okay, let me just back calculate because I have the final expression, but so the final expression is the following. And where this operator T takes three things. That is the previous belief state and current observation and the last action. And this is so PU is the transition probability matrix. And then there is something called sigma, which is all one vector and on the state space. Where this BYU is the diagonal matrix. Where the diagonal elements are 1 y u p x y u. So given the state X or state I, what is the probability that under action U or okay, let's just write U as action. Uh, U, what is the probability that we'll observe the uh, observation state Y? Okay, so let's see what this is. So Y is a vector that gives us the probability of X K equals to 1. So probability that X K equals to X. And this shows the probability that X K plus 1 is equals to 1 given action U and so in more space. Action U and previous state is 1. So probability that Xk plus 1 action U X equals to X. Similarly, probability of Xk plus 1 X. So multiplication of this last two elements gives us basically the probability that Xk plus 1 is equals to 1 to probability that Xk plus 1 equals to capital X. Okay, now this multiplication. So the entire thing gives us the summation of 1 probability that Xk Yk plus 1 equals to Y given Xk plus 1 equals to I, Ak equals to Uk equals to U. Times probability that Xk plus 1 equals to I given information till time K. So what does this mean is, so I'm erasing this second line. And this is the sum is over I. That is the state at current time K plus 1. This is probability Yk plus 1 equals to Y given Uk equals to U and information till time. But what do we want? So here it seems there is some problem. Okay, let me just search few things because so it seems there is some notational problem. It's not clear to me. So earlier P U was matrix. Oh, got it. So here I made a mistake. So this BUY is a diagonal matrix, and there is we'll multiply it with a vector that gives us the probability that A plus 1 is so plus 1 is 1, 2, probability that xk plus 1 is x. So this will give us a vector. Which will be basically probability that yk plus 1 equals to y given xk plus 1 equals to 1 equals to, and so on. Yk equals. Okay, great. So now we use Bayes rule. So probability of A given B intersection C we have, and what we need is, and there is information till time k is also encoded here. So here A is basically yk plus 1 equals to y. B is xk plus 1 equals to x. So this remains. And then C is uk equals to u and the information till time k. So from here we need this we have, and we need we want probability of B given A intersection C. So this is probability of. So this we can write A. What should I write? BI, right? So xk equals to I. And we have for this we have for all I. So probability of, and union of B, so basically BI partitions the sample space. Let's write that as a, that's it. It's BI's partitions the sample space. So probability of A given BI intersection C, probability of A intersection BI intersection C divided by probability of B intersection C. Okay. Now probability of BI given A intersection C is So the numerator you can write, you can use the conditional probability. So this will be probability of A intersection I intersection C. And the numerator, since BI partitions the sample space, so we can write this as probability A intersection BI intersection C. Or so this is some other thing. So this is J. So this is indexed by J, the denominator, and sum over J. Okay, so this is what. Oh, sorry. Still, we have not written in terms of. So we should have written in terms of this, right? Just a second. So instead of this, let us write probability P and then bring the numerator here, probability PI intersection C. And see, this is what we wanted. Sum over G. G. Okay, so yeah, now you can verify that this expression is exactly what probability of xk plus 1 given ik plus 1. Where this is at pi k, yk plus 1. Okay. So sorry for the delay, it was uncalled for. Okay, now the benefit we get out of it is we can now consider this pi k plus 1 is now basically a function of pi k plus 1 and uk. So see that yk plus 1 depends on xk plus 1 and uk, right? So ultimately pi k plus 1 depends on pi k. So belief state is a Markov process or Markov decision process because there is a control element in it. That's but what is the problem? Problem is that here the state space is a simplex, that is a continuous space. So what people can do is they can use algorithms for continuous state. I mean, I'm talking about the learning part of it. They can use algorithms for continuous spaces to learn this MDP. Okay, so people can do planning algorithm are also now much easier to implement. because of this. So you can now just use dynamic programming. Since your actions are finite, it's not a impossible task to do the dynamic programming as well. So let us look at one example, uh, then we conclude today's tutorial. So the example is we'll look at is famous, which is called machine replacement. So say the state space is has two elements, one and two, uh, which is sort of binary. Not sort of, is binary. And state one corresponds to uh, bad machines, poorly performing machines. So it's not bad machine as so current state is bad. So bad, and this is good. So the idea is as you use the machine, a good machine also goes to bad, and as you if you repair a machine, then it transforms a state from bad to good. And so this uh, okay, this is machine replacement. So there will be no repairment. So you can just replace the machine with new machine. But always you have one machine in, uh, you are using one machine. Uh, the action space is also uh, two actions, one and two. So one corresponds to keep using the machine, keep using, and second is replace. Now there is transition probability P1, that is if you are using if you have taken keep using, sorry, there is some problem. Okay, fine. So if you are using a bad machine, then the probability that it will remain bad is 1, and it will be good, that is 0. Very obvious. And if there is a machine which is good, and then you are using keep on using it, then it will be in bad state in the next time step is theta. Theta belongs to some 0 to 1. So theta belongs to 0 to 1. And with 1 minus theta probability, it will be in good state. And P2 is, if it is, so you are replacing. So if it is bad, then it will be good. So, and if it is good, it will be again good. So there is no surprise there. And the point here is this is partially observable. So you cannot observe whether uh, accurately whether a machine is good or bad. So with If it is good with some probability, you may see it as a bad machine or it's in bad state. So again, Y is also good and bad. Or in the observation and B, that is the observation distribution. If the system is bad and the probability that we will see it in bad state is P and we see it in good state is 1 minus P. And similarly, if it is in good state, with probability 1 minus P, you will see it in bad state. And with probability P, you will see it in, sorry, something else, some other parameter Q. With 1 minus Q probability, we'll see it as in bad state, and 1 Q probability, we'll see it in good state. So here you can, you can use it as your, okay, so say your initial distribution is, your, you are in good state, the machine is in good state. And then whatever we have discussed today, you can compute its belief state, right? The using this formula. Let's do it for one round and then we conclude. So phi 1 is T phi 0. Y1 Q0, and yeah, that's it. So say Y1 is good. Good means good corresponds to 2, right? And U0 is keep using. So that corresponds to action 1, right? Yeah. So this will be B BYU. BYU. Okay, so here another thing that is here, your observation distribution doesn't depend on the action. So what we have discussed is more general here. So BYU is here, you have seen action 2, sorry, the observation 2, that means this. So the BYU matrix will be 1 minus P 0 0 Q. And then P transpose U, right? P transpose U. U is 1. So this matrix 1 theta 0 is theta. And your pi is 0 1 in state. Divided by 1. The rest is same. So this is 0 minus theta. Then I'm not writing anything. So 0 and q times 1 minus theta. Okay, this is strange. This is strange because see, this is strange because this is becoming 0 and 1. There might be some calculation mistake. Belief state is also now 0 and 1. So this is sort of impossible. Okay. Okay, there might be some mistake. I'm not going to debug it, but there is some problem. But the formula is correct. I think I have made some mistake in writing these values. It's, okay, so I'm not continuing further today. What you can do is you can debug this problem where I have done this mistake. It's a, I mean, mistake in calculation or writing in proper forms. But this one is correct, this for me. Okay, so that's it for today. Anyone has any question? Okay, I'm assuming there is no question. Okay, thanks for joining.